Hello to everybody. My name is Thomas Heinze, and it's a pleasure for me to present this joint work of Wolfram Amme, André Schäfer and me about our new clone detection method and tool, Stone Detector. For a start, why have we conducted this research on code clone detection? Empirical studies have proven that code reuse and copy and paste are frequent practices, and cloned code can be found in many software projects. The Déjà Vu study in 2017 showed a portion of 70% among the source files on GitHub to be duplicated and reused code. Considering the omnipresence of cloned code, its detection is important for a number of applications. With code, also bugs and vulnerabilities can be duplicated. Detection of code clones allows for searching and finding similar code in code repositories. Clone detection is also important for the application of deep learning on code, as code duplicates present in training and test datasets can introduce severe bias in the trained models. Cloned code can come in many forms, ranging from plain copied code over code where certain variable names or instructions are changed, to code which is syntactically different but performs the same computations. In the literature, code clones are classified accordingly into 4 types, while Type 1, Type 2 and part of Type 3 clones, also known as near-miss clones, can be mostly identified by today's tools. Detection of Type 3 and Type 4 clones is an open research problem. In our work, we have developed a new method for finding more of these Type 3 and Type 4 code clones. To this end, we do not only consider code syntax for finding clone code, but also control flow, and therefore first transform the code into dominator trees. In dominator trees, control flow is given by the dominance relation, stating that an instruction dominates another instruction if the instruction always executes before the other. Since a dominator tree is a tree, we can simply represent it by a listing of the paths from its root to all of its leaf nodes, called description set. An elaborate encoding of the paths in the description set then allows us to apply text-based comparisons for finding similar paths and therefore similar description sets and therefore code clones. Let's walk through our method by way of an example. On the left-hand side of the slide we have a Java method, and on the right-hand side its control flow graph. As can be seen, a control flow graph can contain cycles, which complicates its encoding. Considering instead the dominator tree of the Java method, we can create an encoding by traversing its paths from the root to the leaf nodes, which we call a description set. The elements of the description sets are then sequences of instructions reflecting these paths. In case of our example, we end up with 3 paths in the method's description set. Note that similar to other clone detection tools, for example NiCad, we do not simply encode the instructions, but rather apply some abstraction techniques. For example, all identifier names are mapped to a single symbol, all constants and literals are mapped to another symbol, and method calls are encoded using references to a method lookup table. This results in an abstract description set like the one shown here. Using the description sets of 2 code fragments then allows us to assess their similarity with a distance function. This distance function tries to find an optimal pairwise matching of the paths of both description sets, such that the overall sum of path distances can be minimized. The distance value for two paths can be calculated using string metrics, which are applied to the instruction sequences of the paths, such that included instructions are considered as characters. As a result, we basically perform a text-oriented comparison of the description sets. We have used several string metrics in our experiments, including the Hamming distance, the Levenshtein distance, or also the longest common subsequence algorithm. We will here report, however, our results for the longest common subsequence algorithm, as we achieved the best performance using this metric. We have implemented our new clone detection method in the tool Stone Detector. Stone Detector provides a fully functional clone detector for Java source files. In order to evaluate our method and its implementation in the tool Stone Detector, we have conducted several experiments on the bclone benchmark. Using the benchmark allows us to assess the recall of code clone detection tools, that is, how many of the known code clones a tool is able to find. For a comprehensive comparison of Stone Detector with the state-of-the-art, we have included 6 other clone detectors in the evaluation. Nycat is a state-of-the-art text-based method employing lightweight parsing and pretty printing. Sorcerer CC is a lexical tool which was designed for finding code clones in large code repositories. CC Aligner is another recent lexical clone detector for finding code clones with larger syntactical variants. Dekar is a syntactical tool working on abstract syntax trees, and finally, Oreo is a representative of the recent deep learning clone detectors. As shown on the slide, the experiments confirmed the good recall values of our method and demonstrated that Stone Detector not only finds near-miss code clones at competitive performance with the state-of-the-art, but is also able to detect a significant part of the harder to find type 3 and type 4 code clones. Manual inspection of random samples of found code clones also proved reasonable precision of the tools, including Stone Detector. A notable exception, however, being Dekar, for which we assessed more than each second detected code clone as false positive. Manual analysis also revealed that Stone Detector in particular identifies code clones where the same control flow is implemented using different syntactical constructs, so-called structural clones, and code clones where one code fragment is embedded into another, so-called subclones. In further experiments, Stone Detector proved its scalability on large code repositories. While up to 1 million lines of code can be analyzed in seconds, analyzing 100 million lines of code took 7 hours, which was only beaten by 2 other tools, Oreo also lasting 7 hours, and Nycat requiring less than 3 hours. In this talk, we have presented our new method to code clone detection and its implementation for Java source code in the tool Stone Detector. The method incorporates control flow information into clone detection using dominator trees and matches code fragments by textual comparison of its encoded paths, called description sets. Our evaluation on bclone bench showed that Stone Detector can find more of type 3 and type 4 code clones, in particular structural clones and subclones, at reasonable precision. Thank you very much for your attention.